the oblique collisions of particles with rigid fixed surfaces and how to interpret them for both normal as well as oblique collisions. Okay. So today we come to the final aspect of collisions, which will deal with the oblique collisions between two particles or two bodies. Okay. And then we will see just few more types of examples and we'll be done with system of particles chapter. So let's get underway. Okay, so in this, let's start with a quick recap of the concept of collision of a particle with a rigid surface. So what we had learned is that if the particle collides with an incident velocity, let's say V naught, which is making an angle of incidence with respect to the normal of theta naught, then the incident velocity V naught, it has two important components. Just a second. Yeah, so the incident velocity V naught has two important components. The normal component, which is V naught cos theta naught. That is also the approach velocity. Okay. And the tangential component, which is V naught sine theta naught, which you can just write with this symbol. So after the impact is over, if the particle goes off at a velocity V like this, at a sort of angle of reflection with respect to the normal of theta. So the velocity after impact, that has components V sine theta, which becomes the separation velocity, and V cos theta, which becomes the, V sine theta, which is the tangential component rather, V cos theta, which is the separation velocity, okay. So then we apply the principle that the tangential component is conserved. So V sine theta is equal to V naught sine theta naught, and the coefficient of restitution is the ratio of separation to approach velocity. So from that we get the relation that V cos theta is equal to E times V naught cos theta naught. Okay, so this is what we use for solving this general situation, and you can see that if you just put theta naught equal to 0, you get the special case of the normal impact, and non-zero value of theta naught, like the example I've taken here, is the oblique collision situation. Okay. And we had also seen the two extreme cases of E equal to 1, which shows conservation of kinetic energy, an angle of reflection equal to angle of incidence, and the case of E equal to 0, where the particle gets stuck to the surface and moves along the surface tangentially only. So let's look at a couple of examples based on this today, because this is a very important application situation for JEE Advanced level in particular. Okay, so the first and most basic type of example based on this is a standard projectile bouncing off a horizontal surface like this continuously. So let's see that situation. So if we have fired a projectile at an initial velocity v naught, at an initial angle theta naught, let's say like this, and it makes a partially inelastic collision. So you can see that with each bounce, its range will become lesser and lesser. So this is the first collision, the second, and so on and so forth. So given that v naught is, let us say, 50 meters per second, and theta naught is 53 degrees, okay, and g is equal to 10 meters per second square. If all collisions have coefficient of restitution equal to 0.5, you want to find velocity immediately after first impact. Secondly, if this range is r naught between the starting point and the first impact, and this maximum height in between is h naught, and then between the first and second collision the maximum height is h1, and this range is r1, and then the next one is h2, and this range is r2, and so on and so forth. But to find h1 and r1, and also h1 is to h naught and r1 is to r naught, and we have to develop the general formula for hn is to h naught and rn is to r naught. Okay, so just try out this question.
Sir,
Yes.
sir, could you just show the upper part as well, which
Okay.
which
Sir,
Yes.
sir, we have written this last lecture, na?
Yes, you have written this thing in the last lecture. So now you have to apply this and work out this question here based on this. Okay, so anybody got the first part? The velocity immediately after first impact, this should be pretty easy to calculate. So see what is happening, the projection velocity, you can break it into components. So you can see that the vertical component of the projection velocity this is 50 meters per second and this angle is 53 degrees. So you can see that this has a horizontal component of 30 meters per second and a vertical component of 40 meters per second. So this is the projection velocity. So for the first part, you don't have to do any complicated projection or projectile method at all, projectile motion method at all. You have to just understand that the impact here will happen such that the impact velocity will have the same magnitude v0 and will be making the same angle 53 degrees. So the impact velocity is having a tangential component, which is you can see 30 meters per second, and it's having a normal component, which is the approach velocity, which is 40 meters per second. Just use that property of projectile motion. Now you know that the coefficient of restitution is 0.5. Okay, so immediately after the first impact, what will happen is that the normal component will become E times. So this will become a separation velocity, which is E times the approach velocity. So it will become 20 meters per second, whereas the tangential component of velocity will remain conserved. So that will be 30 meters per second. So accordingly, your velocity after the first impact, let us say that is v1. So v1 as a vector will become 30 I cap plus 20 j cap in meters per second. Okay. Because this projection velocity v0 in component form was 30 I cap plus 40 j cap. Okay. And likewise, now you can see this pattern that after the second impact, if the velocity is v2, v2 will become 30 I cap plus 10 j cap, and like this will continue. So after the nth impact, the x component remains conserved, but the y component becomes 40 upon 2 to the power n j cap in meters per second. So once you understand this aspect, that every time the x component of velocity remains conserved, on impact, because it is tangential. Okay, and the y component, that is the normal component. So for that, we'll use the idea that the separation velocity is E times the approach velocity. Okay. So now using this and the projectile motion concepts, you can find out the other parts of the question, the range and all that. So you can also see if you want to calculate this magnitude, becomes like this, and if you want to calculate this angle, like this.
Sir, applied velocity and separation velocity is along same direction.
Opposite directions, no beta. Approach velocity is into the surface, separation velocity is away from the surface, but they are perpendicular, no? Compare this impact velocity, no? This one here, this is the impact velocity, and then this one here is the velocity just after impact. So see, separation velocity is normally away from the surface, no? Approach velocity is normally into the surface. Is it clear now?
Yes, sir.
So when an object is going and hitting a surface, then this component of velocity, this is the approach velocity. And then immediately after impact, if its velocity becomes like this, then this component becomes the separation velocity.
Yes, sir.
So always the separation will be less than equal to the approach, depending on the coefficient of restitution. If E is equal to 1, then it will be like a symmetric case. But obviously here E is not equal to 1, so it's not symmetric. You can see the separation velocity is actually 0.5 times the approach, because E's value is given to us as half. So every time it impacts, that vertical component of velocity will become half of what it was. So after the first impact, it went from 40 to 20. Second, में 20 से 10 हो जाएगा. Third, में 10 से 5 हो जाएगा. So like that, after the nth impact, the vertical component of velocity will become 40 upon 2 to the power n. Because every impact it's becoming less by a factor of half.
Sir, but X component will remain conserved only, na?
Whereas X component will remain conserved. So you can see in the formula that this is after the nth impact. The X component remains conserved. So which means that, see, practically what will happen is that this is like a geometric series now for the Y component. So 40 upon 2 to the power n. So after a few impacts, like maybe 7 or 8 impacts, the vertical component will become negligible. So it's
Yes,
hardly
sir.
going to move vertically, whereas the horizontal component, because we are assuming the surface is frictionless, it will remain conserved. So instead of bouncing, then it will start sliding along the surface horizontally. So after a few impacts, it will be sliding horizontally.
Sir, if friction was present,
Then when it starts sliding, it will decelerate. So then for that, you know how to apply the formula. The coefficient of friction, if it is mu, the deceleration will be mu g. So you can see
Yes,
that after
sir.
how much time or distance it will come to rest. You can use either work energy or you can use kinematics or whatever.
Yes.
Okay, so now as far as the range is concerned, for each of, like between each of the collisions, so for projectile motion, instead of using the sine theta cos theta formula of range, what you can use is that if you project something with a velocity u at an angle theta, okay, you take the x component of projection as ux and the y component of projection as uy. So this is a very useful trick to remember, that if you solve it component wise, I'll come back to the collisions, but here let's just talk about the projectile motion. So if it goes and hits the ground at time capital T at a range r, and in between it reaches a maximum height of h, then the time of flight is 2 times uy by g. That's how you get the formula 2u sine theta by g. But remember, in terms of component, it's easier that way. Okay, the maximum height is uy square by 2g. Okay, so that's how you get it as u square sine square theta by 2g. But again, for these type of questions, remember it in component form. And the range is nothing but ux into time of flight. So that is the same thing as ux into uy twice divided by g. So that's how you get u square sine 2 theta divided by g. But remember it in terms of the components. Okay. So if you do it this way, then you can see over here that when we apply this concept here, this first range is R naught, let's say, and this is H naught. Okay. So this was 30 and this was 40. Now. So R naught will be ux into 2uy by g. So that is 30 into 2 times 40 by 10, or this is 8, so 240 meters. Okay. And this h naught will be uy square by 2g. So that is 40 square by 2 into 10. So that will be 80 meters. Okay. This is my h naught. Okay. Now when you see this part from the first impact to the second impact, in between the height is h1 and this range is r1. So what is happening is immediately after the first impact, the velocity is becoming such that x component remains the same, but y component becomes e times this, no? Where e is half. So ux remains the same, but uy after the first impact, it becomes, let's say, uy prime. So it becomes e times what the earlier one was. Okay, so now from these two formulae, what we'll understand is that r1 will become e times r0 because it is ux into 2 times uy prime divided by g. Okay. Whereas h1 will become e square times h0 because this is uy square by 2g. So this is how this is affected. So r1 will become half of this, 120 meters, whereas this will become 1/4 of this, so it will become 20 meters. So like that, now if you see the next one, you can see r2 will be e times r1 or e square times r0, but h2 will become e square times h1, so that is e to the power 4 times h0. And like that, if you make the series, the range after the nth impact will become e to the power n times r0. So that is 240 upon 2 to the power n meters. Whereas the maximum height will become e to the power 2n because every time it's changing by a factor of e square. So it will become 80 divided by 4 to the power n in meters. So this is a general formula. And you can see that in this general formula itself, if I put n equal to 1, then I get the specific values of this and this. So that's how in this type of question, it helps a lot if you understand things about projectile in terms of components. Okay, so I'm just taking you to this part first, and I'm showing you the properties of projectile motion in component form. And then we'll come back to the application of that over here. Okay, so just make a note of this section, people. Okay, so now when we apply this concept over here below, so see, first I have applied it for what is happening from the projection till the first impact. Now, this is from t equal to 0 to first impact in this part, okay, which you can see in the diagram above. Whereas this section, what I have applied now here, this is for this part from first to second collision. Okay, and then this is second to third, and then I have generalized it. This thing is from nth to n plus 1. Okay, so this becomes a general formula.
Sir,
Yes.
sir, can you explain that how you found the range of from first collision to second collision?
So see what is happening between first and second collision. You can see that the x component of velocity for projection is the same after the impact is 30 only. So ux is 30, right? But what is happening to uy immediately after the first collision? ये जो projection velocity बन रहा है, उसका y component भी कितना हो जा रहा है? 20 हो जा रहा है, which is nothing but e into 40, where e was half, so it's e times uy. Got it now?
Yes, sir. Yes.
So now see, the formula for range is what? Horizontal component into time of flight, and time of flight is what? 2 times uy by g. So ux is remaining conserved, but uy is getting multiplied by a factor of e. So overall the thing will get multiplied by a factor of e in comparison. So that's how this is becoming 120, because e is half. Whereas if you see the formula of height, that is uy square by 2g. So uy is e times the earlier value. So square hai, so it will be affected by a factor of e square. Is it clear now?
Yes, sir.
Yes, sir.
So after every bounce, okay, the range will become half of what it was in the previous one, but the height will become 1/4, because range gets multiplied by a factor of e, whereas height gets multiplied by a factor of e square. Okay. So if you trace it back to the original one, after the nth bounce, range is e to the power n times, and the height is e to the power 2n times, and that's how we get the general formula. Okay, so hope this question is fully clear.
So 1 minute.
Okay. Okay, so hope you finished with this. Now
Yes,
another typical type of question which is quite important of this type is something like this, where we have an inclined surface So we have an inclined surface like this, which is, let's say, at inclination of 60 degrees with respect to the ground. And a particle is dropped onto it from a certain height above. So the particle makes an impact with the surface. And immediately after the impact, it is observed to have a horizontal projection. So it gets projected horizontally with a velocity v immediately after impact. So if this height from which it is dropped is h, okay, then we have to find out. So a particle p is dropped from a height of h equal to 20 meters onto an inclined surface, okay, as shown. Immediately after impact, it has a horizontal velocity. Its direction of the velocity is purely horizontal, v. So given that g is 10 meters per second square and that angle theta is 60 degrees as shown, you have to find the value of v in meters per second, and we have to find the coefficient of restitution for the impact. Okay, just try this out. So it's the same concept, but the geometry is different. Here the surface is inclined, whereas the impact velocity will be vertically downwards. Okay, and it will be root 2 gh, as you can see from work energy or kinematics. So to figure out that which is the normal component, which is the tangential component, and again apply the normal principle of collision with rigid surface, that the normal component gets reversed in direction and multiplied by factor of e, whereas the tangential component remains conserved. Okay, so that is the concept you have to apply over here. So just try out this question, people. It's quite easy once you figure out what is the normal component and what is the tangential component in terms of directions and all that. So you have done enough of analysis of vectors and this kind of component algebra in Newton's laws of motion also. So it should be fairly easy. Just remember how we used to draw the force vectors in Newton's laws of motion for inclined surfaces. It'll be pretty clear how to solve this. Just try this out. Okay, so the first step is you have to figure out what is the impact velocity and what is the, therefore from that, what is the normal component and what is the tangential component. So let's understand that. So the impact velocity is magnitude, as you must have figured out, is very easy. It is root 2 gh if it's falling through a height of h. So when you calculate that, that will come out to be 20 meters per second. Okay. So we assume the impact is suppose happening at this point. So just before impact, it will have an impact velocity like this, vertically downwards. Let's say V naught. So that V naught will be this much. Okay. Now let's figure out the geometry. So this is the normal line. So you're very used to this from Newton's laws, that if this angle is theta, then here this angle is theta. So you can see that the approach velocity or the normal component will be this one. So this V naught cos theta, this is the approach velocity because this is the normal line. Okay. And this component will be the tangential component because this is the tangential direction. This is the tangent to the surface. Okay. So from this you can see that this has a normal component or approach velocity theta being 60, that is 10 meters per second, right? And this has the tangential component of 10 root 3 meters per second. Okay. Now if we compare this situation to the situation just after impact, so just after impact, we are told that it has some kind of a horizontal velocity, which is V. Okay. So now this angle is theta. And once again, you can see that this is the normal axis, this is the tangential axis. So the velocity after impact, it has a tangential component, which is V cos theta. That is the tangential component. And it has a normal component, which is V sin theta. And that is the separation velocity. Okay. So after impact, the separation velocity is the normal component, which is V sin theta or root 3 by 2 times V, which should be E times V approach. So we have to calculate this, okay? Whereas the tangential component, which is V cos theta, is V by 2. So now you can see that the tangential component should be conserved. So V naught sin theta above should be equal to V cos theta below. So 10 root 3 should be equal to V by 2. That means the speed just after impact should be 20 root 3.
So that first case was before impact. No?
This is before impact. No? I've just made a mistake in the question. The angle theta should be 30 degrees and not 60 degrees. Just change the value of the angle theta to be 30 degrees. I wrote the question wrong. Okay. I'll explain to you why later, that it should not be 60 degrees. Because in 60 degrees, this condition will not be possible, that it will become horizontal after impact. Okay. So just make a correction for the value of theta. Rest everything you can let it be as it is. Just the value of the angle, change it to 30 degrees. Okay. So just make sure you change this value of theta to 30 degrees. So when you change this value of theta to 30 degrees, these two will change. So this will become 10 root 3 meters per second. And this will become 10 meters per second. And accordingly, this here will become V by 2. And this will become root 3 by 2V. Because this would have given us the condition that for the velocity to become horizontal, the kinetic energy is increasing. So that cannot happen. Okay. Kinetic energy should decrease, it cannot increase. So that means the condition is not physically possible that for a 60-degree inclined plane, the velocity will become horizontal after impact. Okay. So anyhow, so this is the conservation of the tangential component. So from this, you will see that V0 sine theta above was 10 meters per second. So this should be the unknown value of V into cos theta, which is root 3 by 2. So V will become 20 by root 3 after impact. So you can see kinetic energy is reduced because V0 was 20 and now it has become 20 by root 3. So the kinetic energy has become 1/9 of what it was. And also substituting this in this formula, we can see that the separation velocity, which is V sine theta, will become 20 by root 3 into sine 30, which is half. So that is 10 by root 3. Okay. So from this, we will get the coefficient of restitution, because we can see here that the approach velocity was 10 root 3 and the separation velocity is now 10 by root 3. So E is the ratio of separation to approach velocity. So separation velocity now we have got as 10 by root 3, whereas the approach velocity earlier we had got was 10 root 3. So we can see the coefficient of restitution as expected is less than 1 because there is loss of kinetic energy. Okay, so it's not that we cannot have a collision for a 60-degree inclined plane, we can definitely have a collision, but that collision will never result in this situation that the velocity becomes horizontal, because it cannot support that condition. You know, for the velocity to become horizontal, if theta was 60 degrees, the kinetic energy should have increased, which is not physically possible. So that will never happen on a 60-degree incline. It will happen on a 30-degree incline. It will happen on an incline of less than 45 degrees, but it will not happen on an incline of greater than 45 degrees. So these type of questions are very important, because what happens is that they test you on your understanding of various things, kinematics, uh, vector algebra, components and all that, and of course the collision concept also. And like now this question can have a third part, that after the impact is over, what is the range of the particle on the inclined plane? So it can also ask you a further question. So this, when you're revising this question later today or tomorrow, you can also solve it this way, that once you've got this horizontal velocity, it's fallen through 20 meters. Now the last part of the question is asking you to find out this thing. That will go on a projectile motion here. So how much is this range going to be? So that is now a pure kinematics question. Okay. So the same question has that projectile on an inclined plane concept also included into it. So that is why these type of questions are very critical for your JEE advanced level. Okay.
Sir, first we can find angle now.
Sorry.
Sir, when you have to find range, we can find first angle.
Find angle in the sense that you have to you have done projectile on inclined plane, no? In
Yes,
kinematics, you have to take your x-axis along the inclined plane, y-axis perpendicular to the inclined plane like that, and solve. So you have to find out what this uy is, what this ux is, and as it goes like this, the acceleration g also you have to divide into components along y-axis and x-axis, and then solve for x and y as functions of time, and from that find the range. Or if you memorize the direct formula, then you can do it from that also. Okay. Okay, so with this done, now let us come to the final type of collision, that is the oblique collision of two particles. Okay, so if we consider a general situation like this, where let's say one mass m1 is traveling at an initial velocity like this, let's say u1, and another body, let's say of mass m2, is traveling at an initial velocity of u2 like this, and suppose we assume that their paths are such that they are going to collide, because it all depends on u1 and u2. No? It may happen that they never collide also, but here we are assuming that it so happens that they do collide. So if they do collide, when they come in contact, okay, what will happen is that the collision impulse that acts between them. So after a certain amount of time, if they are coming in contact over here, let's say, so at a certain point of time, they hit against each other like this, let's say. Okay. So at the time when the impact happens, the collision impulse, as we have discussed earlier, will act along the center to center line. Okay. So this will apply an impulse on this in this sort of direction. This will apply an equal and opposite impulse on this in this sort of direction. And as a result of this impact, what can happen is after the impact, let's say they go off with some velocities v1 and v2. Suppose something like this happens. So after impact, this takes this path. After impact, this takes this path. Okay. So vector wise, what is happening is that this is the impact or collision impulse on particle 1 because of particle 2. And this is the impulse on particle 2 because of particle 1. Okay, so they are equal and opposite. So as far as impulse momentum is concerned, for the first mass m1, the final momentum will be equal to the initial momentum plus the impulse acting on it because of the second one. So this is the collision impulse on m1 due to m2. So that vector diagram will look like this, that if this was the direction of the initial momentum and this is the direction of the impulse on particle 1 because of particle 2, then this will become the direction of the final momentum. So impulse equals to change in momentum. So this is V1. And you can draw a similar vector diagram for the second body also. So for the second body, you can see that the final momentum will be equal to the initial momentum plus this impulse now. This impulse is in this direction here, as you can see. So if the initial momentum was like this, m2 u2, which you can see in this diagram, okay, and the impulse that acted on it was like this, equal and opposite to this one. Okay. So this impulse is negative of this impulse. They are an action reaction pair. Okay, so the final momentum of this one become like this, m2 v2. Okay, so same kind of principle here. So for the system, that is m1 plus m2, we can apply conservation of linear momentum. Which is that m1 u1 plus m2 u2 will be equal to m1 v1 plus m2 v2. So when we write this equation, when we reduce it in component form, it will give us two equations actually. Okay, so next what we'll have to do is we'll express this in component form and solve. Okay. That is how we deal in general with oblique collisions. So this equation that I've written, you can see that this also comes by combining this equation with this equation, that the impulse on the second one is equal to the change in momentum of the second one. And these impulses are equal and opposite. So if you add equation 1 and 2, it will give you the momentum conservation equation. This one that we've written. Okay. So this is the general method of applying the momentum conservation principle, that we write the vector sum of the two momenta initially and equate it with the vector sum of the two momenta after the impact. And from that, we generate two component equations, because obviously the vectors are not collinear. Okay. So basically the important thing is that in an oblique collision, final momenta are non-collinear with respect to initial momenta. That is why it is an oblique collision. So that is why oblique collision is also called two-dimensional collision.
Sir,
Yes.
sir, you have stopped sharing this.
Board is not visible, sir.
Yeah, I know. I'm just resharing it. Okay, the software is just hang for a moment. I'll
Okay, sir.
just a moment. I'm restarting it. Yeah, it's coming back online now. Okay, so this is done. Let's look at an example.
Sir, 1 minute. Not done.
Okay, okay.
Sir, done.
Okay. So now, depending on what kind of data is given to us in a question, it can be something very easy, which can be solved by a single equation, or something little bit more complex, where we have to even use the concept of coefficient of restitution. So we will understand this with a series of examples, how to do the application. Okay. So for example, a very simple version of a two-dimensional collision, but also a very symmetric situation of a two-dimensional collision could be something like this, where we have two identical mass particles, okay, traveling with identical speed v naught, but such that the speeds are like this. If this is our x and y system, okay, then they are inclined in this manner, that this one is at 30 degrees with respect to the x-axis like this, and this one is at minus 30 degrees with respect to the x-axis. So now they go and make a collision somewhere here, and after the impact, okay, so A and B are identical bodies moving at these kind of velocities. So you can see this one will be root 3 by 2 I cap plus 1 by 2 j cap as a unit vector, and this one will be root 3 by 2 I cap minus 1 by 2 j cap. So this information, this unit vector information, is giving you the same thing that the diagram is showing you. Okay, so they are moving at these velocities on a smooth horizontal plane, which we have drawn as our xy plane.
That means initial velocity is same.
Initial speeds are same, but velocities are different because obviously the directions are same. So you can see that magnitude of VA is equal to magnitude of VB, which is equal to V naught, but their directions are oblique like this. Okay, now they make a perfectly inelastic collision. So that means they stick together. So we have to find the momentum or the velocity after impact. So they make a perfectly inelastic impact or collision. So perfectly inelastic means they stick together. So we have to find the final velocity, and whose final velocity they'll combine as a single mass. So for the combined body, we have to find the final velocity after impact. So this is the most simple level of question you can see. Okay. So you can say that if A and B are having masses m and m like this and traveling with velocities VA and VB like this, after the impact is over, they will become one combined mass of 2m moving with some combined velocity v. So all you have to do is momentum conservation, that mva plus mvb should become 2m into the final velocity after impact. So you can see that the final velocity will just become the mean of these two velocities. So you can do it by component algebra above, or you can do it by geometrical approach also. If you do it by component algebra above, you can see that it will become root 3 by 2 v naught I cap. Or if you use geometry, you can see that if you're expressing this equation, that v is equal to va plus vb by 2, or even if you express the momentum conservation equation, that this is one initial momentum, this is another initial momentum. So this is mvb, it is v naught in magnitude. This is, sorry, mv naught in magnitude. This is also mv naught in magnitude, but this is mva. And you can see that the angle between these two will be 60 in all. This angle is 30 and this angle is 30. you remember your geometrical approach theorems, you'll see that when you make the parallelogram for the sum of these two, this becomes a rhombus. So the final momentum, which should be the vector sum of these two momenta, will simply be given by this diagonal now. So this is the final momentum, which is 2mv, which is basically momentum of A plus momentum of B. So if you just apply that vector geometry, you can see here that 2mv will have a magnitude which is of 2 times mv naught cos of 30. So from that you will get the same result, that V has a magnitude of V naught root 3 by 2. Okay. And the direction you can check out from the diagram. It is along the angular bisector of these two momenta. So that is nothing but our x-axis. So this is like a very basic level of an application of momentum conservation in 2 dimensions to solve an oblique collision. Okay, so hope this example is clear. Now let's look at the next level of question we can have. Yes?
Sir, 1 minute, I'm just copying the last point.
Okay, okay. Okay, done, beta?
Sir,
Yes.
sir, can you please scroll up once? Sir, I think I missed something.
Okay, okay.
That note part. Done, sir.
Okay. Okay, now next example, what we have is something like this. There is like a smallish particle, okay, which is moving again on a smooth horizontal plane, we'll assume, with a velocity like this. Get this correct. Okay. So this is a particle of mass m1 moving with a velocity v0, and then it hits another body or a spherical particle or a disc shaped thing or whatever, which is initially at rest. So it hits
Sir,
this.
in
And,
this case, we have to assume XY axis, no?
we have to assume
XY axis.
XY axis you can take according to your convenience. The question is just giving us this information, okay, which I'm going to write now. Then accordingly you can select the axis, whatever will be convenient for you to solve it. Okay, because you will have to select the axis because it will be a two-dimensional problem. Okay, so particle m1, which is of mass, let us say 1 kg, traveling at v0, let us say v0 is 1.8 centimeters per second on a smooth horizontal surface, makes an oblique collision with a heavier body, which you can see with m2, where m2 is, let us say, 4 kg. Okay, now immediately after impact, okay, m1's velocity is perpendicular to its initial velocity. So that basically means that what will happen, that after impact, this one will go off in the perpendicular direction. So after some time, when this reaches here, immediately after impact, it will have some velocity v1, let's say, like this, which is perpendicular to the original direction of motion. And of course, this one will have some velocity v2, which will be in some kind of direction like this. So we have to find, okay, initial velocity like this. Find v1 and v2 if the angle between the vectors v1 and v2 is 150 degrees after impact. That is, as you can see in the diagram, v1 and v2 are at an obtuse angle the way they are moving. Okay, so if that angle is equal to 150 degrees, we have to find v1 and v2. Okay, and also find the magnitude of the collision impulse J. So just try out this question, people.
Sir,
So
means
now-
you have to find final speed.
So you'll have to calculate that now. So that information is given to you. You have to use that. V1 and V2's magnitudes are not given, but what is given to you is that V1 is perpendicular to V0, and also it is given to you that the angle between V1 and V2 is 150 degrees. And also the masses are given. Masses are 1 and 4 kg. So when you use momentum conservation, you will see that you will be able to solve for V1 and V2 because those are your two unknowns, and momentum conservation will result in two component equations. Because you will take x and y axis and write two component equations. So ultimately you will be able to solve for v1 and v2 because you'll have two equations and two variables. You understanding now?
Sir, no, I was asking that only, that we have to find final speed.
You have to find final speeds v1 and v2. Okay, find v1 and v2, and you have to find the collision impulse in magnitude.
Yes, sir.
So just try this out. Okay, so once again, if we take this as our x-axis and this as our y-axis, so we can see that before impact, the initial momentum of our system was like this. So the initial momentum we can just write as
That second mass was at the rest, na?
the second mass was,
Rest at the rate.
sorry, come again.
So rest.
Second one is at rest, yes, initially, yes. Okay, now after the impact, you can see that the first one is going perpendicular to the initial velocity's direction. So we can take that as our, we have taken that as our y-axis. And also it is given to us that the angle between V1 and V2 is 150 degrees. So that will give us the exact direction of V2 also, because V1 is along the y-axis. So if this whole angle between V1 and V2 is 150 degrees, that means this angle here is, this angle here is 60 degrees. So we can write the final momentum after impact as m1v1 plus m2v2. So when we write this in component form, this will become m1v1 j cap plus m2v2 into this unit vector. Unit vector like this at 60 degrees, or actually negative of 60 degrees with respect to the x-axis. So that will be cos 60 I cap minus sin 60 j cap, or like this. Okay, so this is our final momentum. So now m1 and m2 are given, and also v0 is given. So when you just conserve the momentum by equating this initial momentum with this final momentum, you'll see you'll be able to solve for v2, for v1 and v2 both. This is before impact. This is after impact. So next step, we can just apply conservation of momentum for the system. Okay, so that we can do in whichever method is convenient for us. If you want to do in vector form, we can write it as like this. So m1 v naught I cap is equal to, on this side, if you see, it is m2 v2 by 2 I cap plus m1 v1 minus root 3 by 2 m2 v2 j cap, and we can solve this, or we can also do it in component form. So if we apply conservation of momentum in component form, x component of momentum in the first diagram you can see is m1 v naught. In the second diagram you can see it is m2 v2 cos 60, and the y component of momentum in the first diagram you can see 0. In the second diagram it is m1 v1 minus m2 v2 sin 60. So we can solve it as two independent equations like this, or we can just solve both sides of this. So we have m1 v naught is equal to m2 v2 by 2. From this, comparing the x components, okay, and m1 v1 minus root 3 by 2, m2 v2 is equal to 0. Okay. So that's the same as equation 1 and 2. So basically solving, we'll get 1 kg into 1.8 centimeters per second is equal to 4 kgs into v2 into cos 60, which is half. This is what we'll get by solving the first equations. So from this we will get v2 as 0.9 centimeter per second. Okay, and now substitute this in the second equation. So the second equation will basically give us m2 v2 root 3 by 2 is equal to m1 v1. So 4 kg multiplied with v2, which is 0.9 into root 3 by 2 is equal to m1, which is 1 kg into v1. So basically you can see that v1 will become equal to 1.8 root 3 in centimeters per second. Okay, same thing you will get by solving these also. Okay, so hope this is clear, people. And then as far as the impulse is concerned, you can just use change in momentum. So as these two come in contact, this is the impulse on 1 because of 2, and equal and opposite is the impulse on 2 because of 1. So they have the same magnitude, which is what we have asked to find out in the second part. So now you can see that this one is the change in momentum for the second body, which is just m2v2. So this is much easier to solve. Okay. Whereas if you go for this one, this is the change in momentum of the first body, which is m1v1 minus m1v0. Okay. So from this, J should be equal to m1 into mod of v1 minus v0. So whether we go for this or this, it's equally easy. You can see that v0 was like this, and later v1 was like this. So they are perpendicular vectors. So mod of v1 minus v0 will be square root of v1 square plus v0 square, because they are perpendicular vectors. Okay, so that is square root of (1.8) square plus 1.8 into root 3 square. So that is 1.8 into square root of 1 plus 3. So that is 3.6 centimeters per second. So if I go with the more difficult one, which is the second equation here, even that's not so difficult actually. So this impulse's magnitude will come out to be m1 into, so that will be m1 was 1 kg. So we can see that that is 3.6 into 10 raised power minus 2 in kilogram meter per second. Or that is the same thing as for the first one, or rather for the second mass, the velocity is just in this direction, and initially it was at rest. So that was 4 kgs into this velocity v2 we had just seen above was equal to 0.9 centimeters per second. So again it is 3.6 into 10 raised power minus 2 kg meter per second. Okay, but again for JEE it is very important that you should be able to save as much time as possible in each and every question. So it was totally unnecessary to do this second calculation which I've shown here. This one. This was unnecessary. The easier method would have been directly from this. Here I'm doing it just to verify for you that we've got everything correct, because we are getting equal magnitude of impulse on each particle. So that's one way of verifying that my calculations are correct. But other than that, it's not necessary. I could have just calculated the impulse from this. Okay, so we have finished most of the theory portion of this chapter. Next time we will look at some additional concepts like variable mass systems, application of impulse momentum theorem for variable mass systems like rocket systems, etc. But that's a very small part. The major part is the conservation of momentum and applications of collisions, etc. Okay, so you should be able to complete all questions from HC Verma based on what we have done till today. And next lecture we will do some problem solving apart from variable mass systems. So once that is done, you should also be able to cover the exercises in the module, particularly exercise 3 and 4. Okay. So hope you have understood everything in today's session. Very important part of center of mass or system of particles chapter that we have done, particularly the oblique collisions part. Okay. So that's it for today, people. Wish you all the best.
Thank you, sir. Bye, sir.
Bye, people. Bye.
Yeah, bye, sir.
Okay, bye.